All right, so I'm going to start off by finishing this section. Then I'll, this is exciting. Come on. Yes. Okay, so I'm going to finish this little bit of what was a random networks nutshell, and then we're going to talk about generating functions, which is just a beautiful thing. Agreed? Yes. We'll have some fun with those. They allow us to do some really lovely things, thinking about all sorts of counting problems, especially what we're here with random networks. They can be somewhat obfuscatory, though, which is fine. You know, Fourier transforms and things, you go into another world and you sort of play around there and you come back. So there's some magicalness to them. And so we'll see that there are a couple of ways to get to things that, you know, we can use this generating function machinery, generating functionology. And it's very satisfying and beautiful, but we can also do some things in a very direct physical way. So there'll be a mixture, you know, this, and this sort of talks about the literature a little bit, which is a mixture itself. Okay, so, all right, so we went through a whole bunch of stuff about random networks, and I realized for many of you it was a recap, not everyone. Last thing we talked about was this business of your friends being strange, right? That framing, which is really the observation that if you jump on an edge and run along an edge and hit a node, then the degree distribution of that node will be not the underlying degree distribution, right? If you sample by nodes. So that's a really important distinction. And we'll see, we see that actually for Poisson degree distributions, which is every network basically, right? So if you walk up to this box and you pull one out and it's a large enough box, N and M are large enough, then you'll get one with a Poisson degree distribution, right? So you should, I mean, in some sense you might think, okay, let's just think about those guys, which is what we did for 50 years. But the real world doesn't have any of them, so that's a problem. But if you do that with those guys, then these two distributions, P sub k, which is the probability that a randomly selected node has degree k, and R sub k, which is the probability that a randomly arrived at node has k other friends, they're the same. That's just a feature of the Poisson degree distribution. They are the same distribution. It's not true in general. Okay. All right, so we're going to, and I said a lot of this is about contagion, so we're going to think a little bit, start talking a little bit about this before we get into generating functions. You know, this transition, really fundamental thing, phase transition, right? Nothing takes off, or there's no large macroscopic structure in this network, or we can, if it's a dynamic process, nothing is taking off. And then yes, right, so there's some big blob. And in fact, you know, for random networks, you only have to go out for standard random networks, average degree of four friends on average, then you get almost everyone is connected into this big blob, a giant component. All right, okay. So we're just going to go through this and then we'll have a little interlude. So this is one way to think about whether a giant component exists or not. So there's an existence thing, there's the size of it, there are a number of different levels that we can sort of tackle it. But the first thing is there a giant component or not? So lots of words, but basically if we're following a random edge, so we just choose random edge, we do this over and over again, and then if we travel along, we hit a node, and we look at how many other friends it has, and we do that again and again and again. If on average we see at least one other friend, then we're on average seeing exponential growth as we move through the network. And there may be many, many dead ends and so on, but we are seeing this kind of exponential growth, and that will simply just tell us that there is a giant component. And that's it. So this is a condition. It doesn't tell you how big it is, it just says it exists. So that's a good thing to start with. And so for the stuff we've developed so far, that means the average degree of this R distribution, which again is the number of other friends a randomly arrived at node has, if that's greater than 1, then we have a giant component. And so in terms of what we've established, and I don't expect you to remember this, but this is I'm going to say this is an opaque object, right? It's some stuff, you know, and there's no subscript here. This means that this is the second moment according to the underlying degree distribution. This is the first moment or the mean, and this is the mean again. Okay, so if that's greater than 1, then there's a giant component. So that's good. So we can be kind of happy we have like a little test, right? So someone gives you a piece of K, Yeah, let's do that. Right, so just once again, I think I should just write down. So yeah, we've got P sub k, and then R sub k is the probability that we hit a node of degree k plus 1, because we're interested in k other friends, right? K other friends. Think of it like that. And then we'd have to normalize it, and the normalization will turn out to be the average degree. Okay. So, just say again, it's got, as we move from the underlying degree distribution to this edge degree distribution, then we get this factor of a linear factor, right? So if we have a degree distribution, we multiply it by k, it's going to push it a little bit to the right. Okay. Fun times. All right, so second moment's a big deal, and this is this property that we talked about for the strangeness of friends. It's kind of a dangerous thing. So if you have a degree distribution that has some skew in it, and scale-free networks, right, which everyone is now arguing about 20 years later because it's a terrible thing to do. Anyway, heavy tail distributions, let's say, then this is potentially quite large. So, there's this odd thing, because you are, if you have this big skewed distribution of degree, then as you wander around this network, you're going to hit some people with lots of friends. And then, of course, they have lots of friends, and then there's a good chance that they will hit people that have lots of friends. So it takes off. Anyway, so I'm going to say that this is true, but not useful. And, of course, you can play around with it, and you'll see in older papers this kind of thing, or in books. You'll see this in books. People will write this down. This is also true. It's just a rearranging of this. Right? So you could say, okay, here's a test. I've got some P sub k. Find the second moment. Is it greater than the mean? Times 2. Right? Fine. But that's not a very, it doesn't tell, there's not much of a story there, right? It's just a little mathematical test.